Just take a look around you for a second. Seriously, the device you're watching this on, the wires hidden in your walls, even the very air you're breathing, it's all made from a pretty small set of fundamental ingredients. Today, we're digging into the biggest divide in that cosmic pantry, the amazing world of metals and non-metals.
Okay, this sounds like a trick question, right? I mean, one is a solid, shiny ring on your finger, the other is this invisible gas that's literally keeping you alive. So what on earth could they have in common? Well, they share this really deep identity that honestly unlocks almost all of chemistry. The answer is, they're both pure elements. And these elements, these basic building blocks of, well, everything, are sorted into two huge families. Think of it as the first and most important split in the entire library of matter. You've got your metals on one side and your nonmetals on the other. As of now, we've pinned down 118 of these elemental building blocks. You've seen them all organized in the periodic table. But for what we're doing today, you can pretty much just imagine splitting that table right down the middle, based on how they act and what they look like. So let's start with the obvious stuff, the things we can actually see and touch. How can you just, look at something and get a good guess if it's a metal or not? It all comes down to their physical properties.
The difference is pretty stark, isn't it? Over here in the metals camp, things are lustrous. They have that signature shine. They're strong and malleable, which just means you can hammer them into thin sheets without them shattering. And they are fantastic conductors of heat and electricity. That's why your house is wired with copper. But then you look at nonmetals, and they're basically the complete opposite, usually dull, brittle, and they're insulators, which makes them really bad conductors.
But, and this is where chemistry gets really cool. Just when you think you've got the rules all figured out, nature throws a curveball. Check this out. Mercury is a metal, but it's a liquid at room temperature. Iodine is a nonmetal, but it's shiny. And graphite, yep, the carbon in your pencil lead, is a nonmetal that actually conducts electricity. These exceptions are so important because they remind us that these categories are just helpful guides, not some kind of unbreakable law.
Okay, so we've covered the look and the feel, but an element's true identity, its real personality, comes out in how it acts. We're going beyond the surface now to look at their chemical properties.
Picture this. You take a typical piece of metal and you drop it into some dilute acid. What happens? You get that classic fizzing and bubbling, right? That reaction is kicking out hydrogen gas and leaving a salt behind. This is like a signature move for a lot of metals.
No way, not even close. If you drop a tiny piece of potassium into water, you get this crazy, violent, fiery reaction. But if you drop a gold coin into that same glass of water, well, you could come back in 1,000 years and absolutely nothing would have happened. This massive difference in reactivity is one of the most important ideas in all of chemistry.
And this right here, this is the elemental pecking order. It's called the reactivity series. Way up at the top, you've got the rock stars, like potassium. They are desperate to react with almost anything. Then you go all the way down to the bottom, and you find the really chill elements, like gold, which is perfectly happy to just hang out by itself for centuries. This one list dictates everything from how we get metals out of the ground to why your car eventually rusts.
But why? Why is potassium so hyper and gold so laid back? The answer isn't on the surface. It's hidden deep, deep inside the atom itself. We're about to pull back the curtain on the secret engine that drives all of this.
And the secret is something called the valence electron. Okay, so think of an atom like a tiny solar system. You've got the nucleus in the middle, and then you have electrons orbiting in these layers or shells. The electrons in the very last, outermost shell are the valence electrons. These are the frontline soldiers of chemistry. They're the only part of the atom that gets involved in reactions.
Now here's the most important part. Every single atom wants only one thing in life, a full outer shell of electrons. That's its happy place, its state of perfect stability. Metals, they usually only have 1, 2, or maybe 3 electrons in their outer shell. So for them, the easiest path is to just give those few away. They're the generous givers. Nonmetals, on the other hand, are almost full. They're just 1 or 2 electrons short, so they are the eager takers, always looking to snatch an electron to complete their shell.
Let's just watch how this whole drama plays out with regular table salt. You've got sodium, a metal, with 1 lonely electron it would love to get rid of. And you've got chlorine, a nonmetal, that desperately needs just 1 more to be complete. So what happens? That electron literally jumps from the sodium over to the chlorine. Now the sodium is positive, the chlorine is negative, and, well, you know what they say, opposites attract. That incredibly powerful attraction is the ionic bond.
And that super strong bond is what gives compounds like salt their signature features. It's why they form these rigid, beautiful crystals. It's why they have sky-high melting points. You have to pump in a ton of energy to break that bond. And interestingly, they only conduct electricity when you melt them or dissolve them in water, because that's when their charged ions are finally free to move around.
Okay, so this whole atomic level dance between givers and takers is fascinating, for sure. But how does it actually matter in the real world? Well, this knowledge is precisely how we build our world, starting with how we get metals out of the ground in the first place.
This is the key takeaway right here. The more reactive a metal is, the more tightly it clings to other elements out in nature, in its ore. And that means it's going to put up a huge fight when you try to extract it. See? Our old friend, the reactivity series, is back again, but this time it's basically a blueprint for the entire mining and metals industry.
And this lays it out perfectly. For those super reactive metals at the top of the list, like aluminum, you need to hit them with a massive jolt of electricity, a process called electrolysis to force them to let go. For the middle-of-the-road metals like iron, you can get the job done by heating them up with carbon in a process called smelting. And for the lazy, unreactive guys at the bottom, well, gold is often found as pure nuggets. It barely needs any work at all.
So we've spent all this energy and effort to rip these metals away from their natural, stable homes in ore. But here's the thing. Nature always tries to pull them back. And this leads us to a battle we're all fighting every single day, the battle against corrosion.
You know, we tend to think of something like rust as a failure, like the metal is breaking down. But if you think about it from the metal's perspective, it's actually succeeding. It's just doing what it naturally wants to do, which is react with the air and water around it to get back to that more stable, low-energy state it was in when it was an ore.
And you have seen this absolutely everywhere. That familiar, flaky, red-brown rust on a piece of iron, the beautiful green patina that covers copper statues like the Statue of Liberty, or even just that black tarnish that shows up on old silverware. They're all just different faces of the same process, corrosion. But we're pretty clever. We use our understanding of chemistry to fight back. We can put up a simple physical barrier with paint or oil. We can mix metals together to make stronger, more resistant alloys, like stainless steel. Or, and this is my favorite, we can use what's called a sacrificial metal. We coat iron with zinc, which is more reactive. The water and air attack the zinc first, which basically sacrifices itself to protect the iron underneath. Pretty smart, huh? You can literally tell the story of human civilization through our growing mastery of these elements. We went from the Bronze Age to the Iron Age, and now you could say we're in the Silicon Age. Everything we design and build rests on this fundamental divide between the givers and the takers, the metals and non-metals. So it really makes you wonder, as we get even better at this, what amazing new materials will define our future? What will these elements help us build next?